Assalamualaikum. Hai, salam satu Malaysia, salam Perak Aman Jaya, and salam Musibes. My name is Muhammad Fadl Izzuddin bin Amran.
My name is Nur Alisha Balkis binti Muhammad Isa.
My name is Zainuddin Hazin.
And I am Anwar Benedict. Today I will present to you about Chapter 3, Process Management.
Process management.
A process is an instance of a program in education. Batch system work in terms of jobs. Many modern process concepts are still expressed in terms of job. Job scheduling, and the two terms are process memory is divided into 4 sections. The text section comprises and compile program code read in from non-volatile storage when the program is launched. The data section stores global and static variables allocated and prior to executing main. The heap is used for dynamic memory allocation and is managed via call to new, delete, free, and each other. The stack is used for local variable. Space on the stack is reserved for local variable when they are declared at function, entrance, or elsewhere depending on the language. And the space is freed up when the variable go out of scope. Note that the stack is also used for management, maybe language specific. Note that the stack and the heap start at the opposite ends of the process, free space, and grow towards each other. If they should ever meet, then either a stack overflow error will occur or else a call to new or will mail you the diffusion memory available. When the process are swapped out of the memory and later restore additional information must also be stored and restored. Key among them are the program counter and the value on our program register. Process may be in one of 5 stages. First, new. The process is in the stage of the being created. Next, ready. The process has all the resources available that is needed to run, but the CPU is not currently on this process. Third, running. The CPU is working on the process. Waiting. The process cannot run at the moment because it is waiting for some resource to become available or for some event to occur. For example, the process may be waiting for keyboard input, disk access, request, message, terminated. The process has been complete. The let average report by the W command indicate the average number of the process is the ready state over. Process control block. For each process, there is a process control block PCB which store the following types of process-specific information as illustrated. First, process state. Running, waiting each other as discussed above. Second, process ID and parent process ID. Third, CPU register and program counter. These need to be saved and restored when swapping process in and out of the CPU. CPU scheduling information such as a priority information and pointer to schedule queue. Memory management information, page table or segment table, accounting information, user and kernel CPU, time consumed account number limit. Input-output status information, device allocated, open file, table, mention.
Process scheduling. The two main objectives of the process scheduling system are to keep the CPU busy at all the time and to deliver acceptable response times programs, particularly for interactive ones. The process scheduler must meet this objective by implementing suitable policies for swapping processes in and out of the CPU. Scheduling queues. All processes are stored in job queues. Processes in the ready state are placed in the ready queue. Processes waiting for a device to become available or to deliver data are placed in device queues. There is generally a spread device queue for each device. Schedulers. A long-term scheduler is typically a batch system or a very heavily loaded system. It runs infrequently and can afford to take the time to implement intelligent and advanced scheduling algorithm. The short-term scheduler or CPU scheduler run very frequently on the order of 100 milliseconds and must very quickly swap one process out of the CPU and swap in another one. Some systems employ a medium-term scheduler. When system loads get high, this scheduler will swap one or more processes out of the ready queue system for a few seconds in order to allow smaller, faster jobs to finish up quickly and clear the system. Next, context switch. Whenever an interrupt arrives, the CPU must do a state swap of a currently running process, then switch into kernel mode to handle the interrupt and then do a state restore of the interrupted process. Similarly, a context switch occurs when the time slice for one process has expired and a new process is to be loaded from the ready queue. This will be instigated by a timer interrupt, which will then cause the current process state to be saved and the new process state to be restored. Context switching happens very frequently, and the overhead of doing the switching is just lost CPU time, so context switches, state save and restores need to be as fast as possible. For hardware has special provision for speeding this up, such as a single machine instruction for saving or restoring all in register at once. For some hardware, actually has multiple sets of register, so the context switching can be speeded up by switching which set a register is currently in use. Obviously, there is a limit as to how many processes can be switched between in the manner making it attractive to implement the medium-term scheduler to swap some processes.
Operations on processors. The definition about the operations on processors. The processes in the system can execute concurrently, and they must be created and deleted dynamically. Thus, the operating system must provide a mechanism for process creation and termination. Okay, I will tell you about process creation. A process may create several new processes. We have a create process system called during the course of execution. The creating process is called a parent process, whereas the new process are called the children of that process. Each of these new processes may in turn create other processes. In general, a process will need certain resources such as CPU time, memory, files, input-output device to accomplish its task. When a process creates a subprocess, that subprocess may be able to obtain its resources directly from the operating system, or it may be constrained to a subset of the resources to the parent process. The parent may have to partition resources among its children, or it may be able to share some resources such as memory or file among several of its children. Restricting a child process to a subset of the parent resource prevents any process from overloading the system by creating too many sub-processes. When a process creates a new process, two possibilities exist in terms of execution. First, the parents continues to execute concurrently with its children. Second, the parent waits until some or all of his children have terminated. Second, process termination. A process terminates when it finishes executing its final statement and asks the operating system to delete it by using the exit system call. At that point, the process may return data output to its parent process via the wait system call. All the resources of the process, including physical and virtual memory, open file, and input-output buffers, are allocated by the operating system. Termination occurs under additional circumstance. A process can cause the termination of another process via an appropriate system call. For example, abort. Usually, only the parent of the process that is to be terminated can invoke such a system call. Otherwise, users could arbitrarily kill each other's job. The parent therefore needs to know the identities of its children. Thus, when one process creates a new process, the identity of the newly created process is passed to the parent.
Inter-process communication. Independent processes operating concurrently on a system are those that can affect other processes or be affected by other processes. Cooperating processes are those that can affect or be affected by other processes. There are several reasons why cooperating processes are allowed. Information sharing. There may be several processes which need access to the same file, for example, pipelines. Computation speed up. Often, the solution to a problem can be solved faster if the problem can be broken down into sub-tasks to be solved. Modularity. The most efficient architecture may be to break a system down into operating modules. Convenient. Even a single user may be multitasking, such as editing, compiling, printing, running the same code in different windows.
Examples of IPC systems. The first example is PO6 shared memory, the 8th edition version. The first step in using shared memory is for one of the processes involved to allocate some shared memory using SHM-get. Any process which wishes to use the shared memory must attach the shared memory to their address space using SHM. Then processes may access the memory using the pointer written by SHM. For example, using sprintf. When a process no longer needs a piece of shared memory, it can be detached using SHMDT. And finally, the process that originally allocated the shared memory can remove it from the system using SHML. The second example is PO6 shared memory, the 9th edition version. The 9th edition shows an alternate approach to shared memory in PO6 systems. Under this approach, the first step in using shared memory is to create a shared memory object using shm_open bracket in a fashion similar to other file opening commands. The name provided will be the name of the memory map file. The next step is to use the size of the file using ft_run_cat. Finally, the mmap system call maps the file to a memory address in the user program space and makes it shared. In this example, the process that created the shared memory will be writing to it. The third example is mark. Recall that the mark kernel is a microkernel which performs few services besides delivering messages between other tasks, both system tasks and user tasks. Most communication in mark, including all system calls and inter-process communication, is done via messages sent to mailbox boxes, also known as ports. Communication in client-server systems. The first one is sockets. A socket is an endpoint for communication. Two processes communicating over a network often use a pair of connected sockets as a communication channel. A socket is identified by an IP address concatenated with a port number. Remote procedure calls, RPC. The general concept of RPC is to make procedure calls similarly to calling on ordinary local procedures, except the procedure being called lies on a remote machine. Implementation involves stubs on either end of the connection. The issue is identifying which procedure on the remote system a particular RPC is destined for. Remote procedures are identified by ports, though not the same ports as the socket ports described earlier. One solution is for the calling procedure to know the port number they wish to communicate with on the remote system. This is problematic as the port number will be compiled into the code and it makes it break down if the remote system changes their port numbers.